Hello, everybody. This is a new audience for me. Usually, I'm doing the other type of robotics, not the type of robotics that people before and I presume after me gonna talk about. But I'm gonna try to give you a little bit of an overview of what are the achievements and what are the limitations of robotics as we go along. So, the very first question is why robotics, and this answer is different depending on the answer to this question is different to whoever is asking the question. So for me, robotics is a fascinating field because we have some amazing capabilities now. We have robots that are operating on another planet, on Mars. We have robots operating at the bottom of the sea doing stuff and collecting observations. And also we have robots in 5 million households and counting around the world in the form of Roomba. Oops. This is a little, wait a sec, technology here. This little robot here, it's a vacuum cleaner, it's a robotic vacuum cleaner. It doesn't, there is no consciousness most likely on this robot, but it has certain behaviors that associates with different conditions. So I don't know, maybe it does have some sort of Roomba-like consciousness. But the important thing is actually we are having robotic products, and a product, in order for something to be called a product, it has to be not outside of a lab in a significant number of places. So robotics is an important field, and as we go along, I'm going to talk also about basic problems in robotics, more exotic problems in robotics, and also a very fundamental distinction which we're going to come over and over, the distinction between robots as tools for doing something and robots as a mechanism for understanding things. So my presentation and a lot of the advances that we're going to see are focusing on the robot as a tool. And we're going to see that suddenly this robot as a tool has a lot more capability suddenly from basic mechanism, because we can hard code or create behaviors that are more important. So in the very first blog entry, there was this text about consciousness, and there was the question is to feel anything at all, a pinch, a puff of air, the sound of a distant train, or the sight of a rainbow. And the question is, do robots can do that? And I would claim that at least these things they can feel. For example, Robonut over there felt my pressure from my hand and gave a handshake to me. So it felt the pinch, it felt the pressure from my hand. A puff of air, that's an easy one. Every airplane has pitot tubes that they find the pressure of the air, so they can definitely sense a puff of air. The sound of a distant train, you can get an array of microphones and get not only the sound of a distant train, but also the direction. And finally, the sight of the rainbow. Cameras can give you a lot of stuff. Here is the robot's eye view, or as the robot is walking from the seaside and going into the water, and the waves are moving it around. So robots have these capabilities, which I would define as we have sensors on one side that detect, they feel what's going on inside and outside the robot. Then we have actuators that act on the world, and we have in the middle something there which, you know, sometimes we call it a planner, sometimes we call it a brain, sometimes we call it a mind, you know, not often, but there's something up there that connects these two things. And of course, the world is somewhere in this equation too. So in general, most robotic systems, they operate in a tight loop of sense, plan, and act. So when we come into sensors, I would like to bring to your attention that there are two different types of sensors. There are sensors that we call proprioceptive sensors, that they monitor the state of the robot. So these things include the position of the robot, how far it has moved, with what acceleration it is moving, with what angular velocity it is moving, but also other states. For example, the battery voltage, which, if we were to do an anthropomorphize, would be how hungry the robot is. Way back then, one of my very first exposures to robotics was a Japanese fellow in 1996, which he had a regular, trash can-like robot, which have put 3 light bulbs, red, green, and a yellow. And when the robot was running low on battery, it would flash the yellow light, which meant it was hungry. And when the robot had good battery and was moving happily along its way, it would have the green light, which was it was content. And when the robot was blocked somehow, for some reason, usually by a human, it would flash the red light bulb, and this was angry. That's a kind of simplistic, but this robot was having sensing the environment, and it was having certain feelings, and it was going along. Now, I don't particularly like the simplicity of it, but it gives you an understanding of what's going on. So as I was saying, we have proprioceptive sensors that looking inside the robot, looking the state of the robot, and then we have exteroceptive sensors. And I would like to point out that the exteroceptive sensors we are having, in a lot of cases, are a lot more capable than the sensors a human has. For example, we can have like chemical sensors that they can sense chemicals with very high accuracy. We can have LiDAR sensors, all sorts of different camera sensors. And one advantage and one actually point that I would like to bring to your attention is that as technology advances and the sensors become cheaper and more widespread, that allow us to work with a lot more sensors and and do stuff that we were not able to do before. One simple example is the Kinect. Over here, this thing from the Xbox 350. It came about a couple of years ago. It gives you not only an image, but also gives you depth information. And like 3-4 years ago, if you have gone to any roboticist in the world or any vision person, you would say, how about a sensor that gives you both depth and color information? Would say, whoa, that would be a great idea. And you say, how about for $150? They would be like, stop joking, this thing would be $10,000. Well, thanks to the people that play video games, we were able now to have this thing, and it opened up a whole new area on the tasks of perception. Now we can have vision information in the computer on how things look like, not only color, but also where they are located in the world. So in the problem of perception, there is sensing the world, and then there is understanding the world. And I would say that understanding, which was also assigned as part of feeling, is one of these things that we are lacking. We are working on still. Sensing the world, it's like feeling the world. A robot can feel it. It can get all sort of information in. Understanding, it's a different story. So I would like to bring your attention to 3 fundamental problems, 3 fundamental questions in robotics. So the very first question that anybody who works in robotics has to deal with is how to go from A to B. It's called path planning or motion planning. How do we move the robot? How the robot would move around? The second question, and these 3 questions that I'm placing are in no particular order. People are dealing with any one of these 3. Usually they focus on one of these 3, but then the other ones come into play usually. The second one is, what does the world look like? And this is the problem of mapping, as it's called in robotics. The idea is that we take sensory information from various positions and we integrate the measurements to produce a map, a unified view of the world. And usually when it's mapping by itself, we assume perfect knowledge of the position, perfect knowledge from where we took these measurements. And the third problem is, where am I in the world? Localization. So the idea is that we want, if we know what the world looks like, we want to locate ourselves in the world. And this problem assumes that we sense the world and we relate the sensor readings to the world model. And of course, this assumes a perfect world model. Of course, in robotics, like in a lot of other fields, nothing is perfect. So usually we run into these two last problems together, and it's a problem that have seen thousands of publications up to now. It's called SLAM. It was a very catchy acronym for the person that found it. It stands for Simultaneous Localization and Mapping. The problem is, if you have uncertainty on both your position and the world, how do you bring these things together? So I talked about maps, I talked about robots, I talked about the environment. It is a good idea to break it down a little bit depending on the application, depending on what you want to do. Usually you have 3 different components and you can pick and choose from them. So for example, when the world, the environment the robot is going to operate in, it's going to be a simulation, a virtual, an abstract thing. It could be, like as we saw earlier, a robot that has a few rays of sensing and objects dropping from the sky in front of it. This is a very basic abstract world. It could be indoor environment if it goes around in the corridors. It could be outdoor. It could be operating in a 2D scene, like, for example, it operates on the floor or on top of a tabletop. Or it could be 3D, or it could be operating on a terrain. The world could be static or dynamic. It's a big difference if things stay where you first saw them, or if things move around, as we're going to see a bit later. Equivalent, the robot could be a mobile robot operating in indoor or outdoor. It could be walking, flying, swimming robot. Like usually when you have different modalities, you are looking at different types of information also. It could be a manipulator, just a simple robot arm. Well, not so simple, but... Or it could be a humanoid that is a mobile unit that it also walks, and it has manipulators, and it has all sorts of degrees of freedom. Finally, the map, what the robot is going to use, it can have different qualities. It could be a topological map. Like, for example, if I give you directions to go to another location, usually I would tell you, follow this street down that road, on the 3rd block, take a right, and continue for 5 blocks, and you'll be at the restaurant. So that's a topological representation. Could be metric. I can tell you, like, walk exactly 325 meters and then take a 90-degree turn. Not very useful for humans. It could be feature-based. I can tell you, when you see this big landmark, do something, and all sorts of things like that. So we can have all these 3 components, and how do we decide to solve these problems? It depends on what kind of combinations of these 3 parameters we are having. In the next, I'm going to give you an example of these 3 problems and give you some illustration of some algorithms, just so you get a feel of what the robotics community is doing in order to solve these problems. So mapping, as I said, what the world looks like, we can have several different representations. It is related to a more general problem that is knowledge representation, which is very common in AI and in computer vision. And one important question to ask yourself is, who is the end user? if the end user is another robot, maybe you want to have very accurate information, metric information. If the end user is a human, maybe you want to go topological. So the type of maps that you are produce about the world are sometimes related to the end user. And for example, if the end user is a robot, it is very important that your map facilitates path planning, moving in that world, moving through that map, learning how to move in that map. If I give a robot a set of pictures like this, the robot has no idea where it should go. If it should go down this path, I mean, like, we can try to make some ideas like that, but is this a wall? Is that a picture of a wall? Things like that. So consider this very simplistic environment that has, like, obstacles in the dark areas. It has some features. We not quite know what they are. We can have different maps. We can have grid-based, so we can discretize the world. And I have to tell you that computer science people love discretizations because computers are operating in discrete worlds. We can just add the features, or we can make an abstraction of the topological representation of the free space. Or we can create another discretization, not as dense as this one, but we can just put geometric elements. Another type of robotic, of mapping, of environmental representations that have gained prominence the last few years is the idea of appearance-based maps. The appearance-based maps are dealing with images. So what the world looks like in this area, and when the robot moves along for a little while using only vision, how far it have moved. And more important, when the robot goes around in a loop and it finds this area again or over here, when it reaches that same place again and again, does it recognize that it came to the same place? This problem is usually called the loop closure problem. Here's an example of successful loop closures, like areas that were recognized as the same, this area and this area, even though this huge truck passed by and hid all this structure over here, the robot was able to identify that these two places are the same. And the same thing here, even though you have an obstacle here, a car here, the robot was able to identify that these two places are the same. But also sometimes things fail, and fail in funny ways. Here, these roundabouts are about 10 kilometers apart in England, and they look fairly similar, and the structure they have, it's fairly similar. Of course, you can see they're not the same place because there are houses here that are not existing here. So the robot unfortunately thought that these houses were insignificant. And over here, this is a funnier one. This same van passed by the robot in two different locations. And because it passed nearby, the robot says, "Oh, I'm in the same place." So, that gives you an example of the capabilities on one side and the weakness on the other side. And the take-home message I would say from that one is that no single solution, no single technique is the answer. So with that, as I said, creating mapping, we already started talking about localization, finding the same place in the world. So there are three different types of localization. The first one is tracking. Assuming you're starting from a known position, track your progress in the world. And this thing has been studied extensively, especially in World War II and in the military, because you see some incoming object, you want to track its trajectory, know where it's going to strike, or try to intercept it. But also when a robot starts, if it says, okay, I'm on my charger and I'm going to start moving and exploring the world, you can believe that when it is charging, it is in the charger, so it knows its position. The second problem is global localization. unknown initial position. The robot is turned on, starts up, where am I in the world? Very challenging problem. And finally, the third problem, which I think it's kind of funny, is the kidnap robot problem. So the robot has an incorrect known position. The robot believes that it knows that it's somewhere, but it's somewhere completely else. And you're going to say, well, that's kind of nonsense. Why on earth you would think of a kidnap robot? Like, people don't kidnap robots, and if they kidnap robots, that's not exactly. Well, this was an intellectual curiosity for several years as a problem until the RoboCup tournaments started happening. RoboCups it's tournaments that have become quite popular, which a bunch of robots are playing soccer with each other. The problem in the RoboCup tournament is that at certain points the referee moved in, grabbed one robot, and moved it to a completely different place because there was something happening in the game. And this was literally the hand of God coming down and picking up the robot and moving it somewhere else. And the robot was likely going along, trying to, knowing very well where it was, trying to get to the ball, and suddenly, boom, it's somewhere completely else. So even something as abstract, as weird as the kidnap robot problem, it can have practical applications. So just to give you a very, very intuitive understanding, the robot is, in some initial state, it could be anywhere along this area. It detects nothing, so it has not quite a clue where it is. Then it detects a landmark, detects a door, and says, oh, look, I'm in this, I can't be in front of any of these three doors. And then the robot moves a little bit farther, and it says, well, I'm kind of lost. I could be in anywhere on these three places. But then it sees the second door, and it knows, because it was only that much apart, that it have found the location. Of course, it assumes that it knows the map. As I said earlier, the localization problem assumes you have a knowledge of the world in order to localize inside it. So this is a general problem of, you can see it as state estimation, what the robot state, and it depends on the robot. Remember I said earlier on about the world, the map, and the robot could be 2D, 3D, where it is. So for example, for an indoor mobile robot, usually knowing in its XY position and its orientation in the world is enough. If it is a swimming robot like this one over here, then it needs to know its position in X, Y, and Z, and also its attitude, roll, pitch, yaw. And of course, if we have a manipulator like over here, we can define its position, its pose, as the sequence of the angles, like how much its joint is bent, or we can define it very similar with the 6 degree of freedom mobile vehicle as the point of the end effector. So I don't really care where the heck is my hand, as long as my end effector is pointing to the same position. So the majority of work that in localization up to now is dealing with Bayesian filters. It's on a Bayesian framework, and the question we want to answer is, what is the probability of the robot being at position X given all the data we have? And that could be sensor reading, such as range from different obstacles, odometry information from encoders, actions that we take. And this is a general formalism. The Bayesian filter doesn't require that you have a specific probability representation, and it recursively computes the belief. What is the belief for the robot being at position T, given all the data that came before that? So just to give you a cartoon version again, the robot has an initial belief of being here. In this case, we have modeled it as a Gaussian. The robot takes an action of moving forward, and this is the posterior belief after an action. Keep in mind that usually after we take an action, we kind of lose track of where we are. And then when the robot is taking a measurement of some known landmark here, then we are using the posterior belief by using that measurement and the prior belief, and we're getting a much better understanding of where we are. As I said earlier, the problem usually is that we do not have a very good understanding of where the world is, what the world looks like, and where we are. And for this reason, we are combining these two pieces of information together in a probabilistic manner, and we forward an understanding of both our position in the world and what the world looks like. And this is the beautiful problem of SLAM. So I'll just give you a quick example, well, hopefully it will be quick, of underwater pose estimation. This is some work we have done using an underwater vehicle, and we'll combine information from an inertial measurement unit. Actually, I should be pausing it. We are combining information from an inertial measurement unit that gives you orientation and angular velocities and accelerations, and also from a downward facing camera. And the problem is that when we're talking about underwater, the vision is a lot more challenging than it is above water. So for example, we have limited visibility because of haze, we have lighting variations, we have backscatter, like things looking there. Sometimes we pass over patches of sand which will have not many features, and finally, as we go deeper and deeper, we're getting light absorption, so we're losing colors as we go deeper. Oh, that was not nice. So we're instructing the robot using on the camera by giving it some instructions using some micro tags. Here is one of my students, Florian. He's showing the tags on the robot. As you can see, it is not quite that easy to stabilize down there and so present that. And then the robot goes ahead and goes over the coral reef in different trajectories. Keep in mind that we have put some tape down there to ensure that we have some notion of ground truth. And so what do is we are using the inertial measurement unit to propagate our state forward, and so as we go along we monitor our position of the IMU, and also we're taking pictures at different locations. So then we're finding features in this from these locations. The same features can be seen in different locations, and then we combine these features to find the 3D position. Here is an example as we're tracking the features as we go along over this. You can see the tape here on the side, and as we're going along, the features are being propagated along, and the robot is moving forward along its trajectory. As you can see, the robot keeps moving. Sorry, it goes now at 4 times the real speed. Otherwise would have been way too boring. The robot takes a turn around that coral place, and it follows along. You can see that as we go along, we pretty much track our trajectory as we go along, and this is because we are able to combine information from a proprioceptive sensor, the IMU, that tells you what is your accelerations and your angular velocities, and an exteroceptive sensor looking at the world outside. And this data were collected in 2011. More recently, we took, last January, we took the robot and ran it on over a shipwreck in Barbados. So the idea is that with this kind of technology, we would be able to eventually model shipwrecks and other interesting structures underwater. The robot takes a right-hand turn and goes along. Also, we did experiments over coral reefs and another area which would be quite important for environmental monitoring. So, as I said, this is a lot of the stuff that we are capable of doing is robot as a tool. I would not claim that this robot at this position has consciousness, but it's quite capable of sensing and making decisions on its own and also detecting its own state. So finally, motion planning, the third problem, going from A to B. This could be from a toy example, like a world, like a polygonal world, find trajectories over here, or to more important things, like, for example, when you do Mars exploration and you have a 3D model of the terrain that you move along, finding trajectories on this terrain. Here is an example of an algorithm. One of the very first approaches for doing path planning, it was like, okay, assume that the only thing I know is where is the destination where I want to go, and also if I bump into an obstacle, I can sense an obstacle, like very close by. So in that case, I would go towards my destination. When I bump to an obstacle, I'll go all around. When I have circumnavigated completely this obstacle, I know, that was the obstacle. Let me go to the closest point to the destination by going around this obstacle and then continue. And by doing these things, I guarantee that it's a very, very basic algorithm that would guarantee that I would I would reach my destination. Another idea, going very close to the obstacles, it's kind of challenging because usually you bump into them. So the other idea is that I stay as far away from the obstacles as possible. I'm using a structure called the generalized Voronoi graph, which means the areas that are equidistant from different places. So the robot moves away from obstacles until it's equidistant from two obstacles. Then it follows this trajectory, and then when it reaches an area where there is a junction, it decides where to go next. It keeps going on and finds and goes around the environment like this way. So this way, this robot would stay as far away as possible, and therefore would be very safe. Other ideas treat every obstacle as a charged, negatively charged element, and you are also negatively charged, so you are repelled from every obstacle and you are attracted to the destination, so that you can create potential fields that guide you smoothly. A problem of this technique is that it is very easily to construct worlds that the robot is going to be stuck, because it would be all the forces would negate each other. Simple solutions to that, but just to give you a feeling that these kind of problems are any solution. There is not just a single solution. There are multiple solutions. Of course, anybody that have been poor student and have moved out of a small cramped apartment and they had a big couch that they didn't want to lose because they didn't have much money to buy another one, knows the problem of moving. So, the motion planning, path planning could be quite challenging. So, for example, here is an example of moving this couch over here over this weird configuration, or equivalent, moving a robot arm, trying to reach behind some area and do something. Techniques have been used. One common technique called rapidly exploring random trees, where you pick random points in the areas that you can go and you connect them through a tree and you actually travel through, have been used to solve fairly complex path planning problem. For example, this thing, it needs to be moved in a very particular way, otherwise it's going to get stuck. So solving this kind of puzzles or complicated motions have been used using these techniques. So I hope I gave you a feel of what are these three fundamental questions in robotics that most of us are dealing with. And I would like to bring you a little bit, to give you also a bit of a historical perspective and where I think the field is going a little bit. So robotics started with factory automation. To a large extent, people were very interested on moving industrial manipulators to do welding in a fast manner. So this was started in the 1950s, and it continues up now because it's kind of useful. Then later on in the 1990s, we started trying to do mobile robotics. I mean, of course, there was independent researchers, like a few researchers that they were trying to do these things every so often, but I'm talking about where the field was moving in general. So in the 90s, people started moving a robot inside an environment. They usually had sonar sensing. You can see the spurious sensing that was coming around, and the robot is losing track of its position because it doesn't have a very good ability to localize, but you can see that this is not exactly the right map. This is using the sonar sensing, and this is having a camera on top of it to monitor what is seeing in the world, an omnidirectional camera. And now, since 2000, the field is moving more and more into outdoors areas, into field robotics, capable robots that are doing a lot more interesting stuff. So, for example, here is an example from an unmanned air vehicle that we are flying and do some tasks on visual coverage, on how do you fly a robot to monitor what's going on in the environment. For example, if you want to detect over a forest for forest fires, or for detecting diseases or things like that, or an underwater robot which is being here teleoperated to follow a school of fishes. So I would like to bring in this area of field robotics and where the things go down, some of the things that I would say the important questions that, how am I doing for time? Okay, we have space robotics, which is quite fascinating. I would say this is one of the areas where, like we've had sent successfully robots to another planet, and they go there and they detect things and they give us information about that. I think this is quite a technological advantage. We were able, on the other side, to send a robot down 3-4 kilometers down at the Titanic and construct accurate representations of what the shipwreck of Titanic, one of the most iconic shipwrecks, looks like. This is a fascinating video that of mini quadrotors that are flying around and do all sorts of acrobatics, and not only flying around by themselves, but also flying around in formations, multiple of them. The capabilities of these things, and this is only in the last 2-3 years that we are having these capabilities, it's fascinating. Like you can see these robots moving around in different formations, flying up and down. This problem, these are definitely not conscious robots. They have a very sophisticated system of sensing in order to, from outside, locate where they are. These robots cannot know where they are by themselves. So, but it is quite impressive when you see them flying around like that. Autonomous, driverless car driving, very important. Lots of people have done lots of work. DARPA Grand Challenge started 2,040 kilometers from the Mojave Desert, outside of anybody. We just want the robot to be able to drive. Then DARPA Urban Challenge, having a robot moving inside an urban scenario with other vehicles, ensuring that it stops on intersection and things like that. And this is quite impressive. And now we have the new DARPA Grand Challenge, which is a robot has to get into the car, drive the car to a site, get out of the car, walk over rumble, remove debris blocking an entrance, open a door and enter a building, climb an industrial ladder and traverse an industrial walkway, use a tool to break through a concrete panel, locate and close a valve near a leaking pipe, and replace a component such as a cooling pump. Well, you know what? Maybe it's right to laugh, but I would like to point out that when the first Grand Challenge happened, they were supposed to drive 240 kilometers. The first year, the best candidate, Sandstorm from CMU, only traveled 12 kilometers, less than 12 kilometers, and it got stuck on a rock. The next year, 5 robots managed to do it. So I'm not sure if next year, when the DARPA Grand Challenge, this Grand Challenge is going to be successful, but I would like to say that in a few years, this is the type of abilities we're going to be talking about. Driverless cars, Google has traveled 282,000 kilometers as of May. In Nevada, you can get driverless car licenses. And finally, I would like another trend is mobile manipulation, obviously. To paraphrase a philosopher of the 19th century, the robots have only interpreted the world, slam, in various ways. The point is to change it. That's where we're moving to. So, finally, few questions and ideas. Specialized tools versus ROSUM's universal robots. That's the first time the term robot was used. Are we talking about a robot that would be a human-like robot or a specialized tool that have partially exhibiting certain consciousness levels? Sensing versus understanding. Of course, they both fall under the term of feeling, but I would claim that these are not exactly the same things. A lot of work is being done, as you saw earlier, on robots as a tool for understanding intelligence or consciousness. And in that case, I would say that we are still searching for an architecture for intelligence, searching for an architecture on how to put things together. There is robotic technology everywhere, from your toaster that it was told that it doesn't, we were told that it doesn't have any consciousness. More and more robotic technology goes there that makes the robot being, the toaster being a little bit more conscious about the needs, possibly of the user. Moving to collectives of robots, and also keep in mind that as the costs decreasing, we're going to have more and more robotic technologies, and more people going to start playing with them, and we're going to have more things happening. And I leave you that with these 2 videos. This is, on this side is, we don't have an encounter with octopus, but we have an encounter with a lobster here. So the robot was being teleoperated. We sat down in front of the lobster, and the lobster went and checked us out. And the lobster clearly is curious what's going on here, and somehow didn't like what it was seeing or feeling. And you can see that the lobster was like, okay, that's it, I'll fight you. Thank you very much.